Good morning, everyone. Thanks for the introduction. Really excited to be here today to discuss how we can craft better binary classifiers. I would like to share with you some techniques for feature selection and hyperparameter tuning that I found particularly useful in developing more robust and more efficient models. But before we deep dive into this, I must confess that when I was thinking about this talk and preparing my presentation, I actually asked myself, in today's era of Gen AI, is it still worth discussing such methods and techniques for more traditional machine learning models? Well, chances are that most of us have at least one machine learning model in production, saving the day and bringing some good value to our companies, right? So I think this in itself is already a good reason to keep investing and exploring such techniques and methods. So I really hope that this talk can give you some nice insights so you can eventually apply to your own projects and your own models. Now let's see what are the challenges that we are aiming here by optimizing these two key steps within our machine learning pipelines. And when we look to a typical machine learning pipeline, we see that it's composed, of course, by several steps that are required to build a machine learning model. Among these steps, feature selection and hyperparameter tuning are really crucial ones. But yet, sometimes we overlook them because they can be either too complex or too time-consuming, or eventually there are so many techniques that we can simply don't know from where to start. So the question here is, how can we optimize these two key steps and make them more efficient and clear so we can, in fact, optimize our models? Let's starting then answering this question, moving through our pipeline and see the first key step here, which is feature selection. So before we start talking about the techniques for feature selection, it's important for us to discuss actually why feature selection is important, or what are the dangers of having too many features in a model. We can answer this question, or we can tackle this question from three different perspectives. So from the model perspective, we can highlight performance, because too many features in a model can eventually introduce some noise and then can lead your model to overfit, and this is not desirable. And also, explainability is also an issue, because if you have too many features, it becomes harder to identify, for instance, which feature contributed the most for a particular prediction. Also, from the infrastructure side, speed and cost is also an issue, because the more features you have, the more computational complexity you introduce while you are training or even predicting your model. So you require more computational resources, and this can increase your overall cost. And also monitoring, because maintaining and monitoring a model in production with too many features can be quite challenging, because we might eventually lose some interesting signals, or eventually we might overlook some drift that is happening with some of the features. And finally, from the business perspective, documentation is also something really important, especially if your model operates in a highly regulated environment, like in banking industry or health industry, because you eventually need to provide lots of details about your features, and having too many features can become like really cumbersome. And finally, communicating your models, a complex model to your business stakeholders can be also challenging, especially if your stakeholders doesn't have a strong technical background. So yeah, this can also be a challenge from that perspective. Now that we understood a bit the importance of why we should do a proper feature selection in our machine learning pipeline, let's see some techniques on how we can do that. I personally like to group the techniques in 4 different groups. The first group actually is some data cleaning that we usually do to refine our data, to avoid some inaccuracies and avoid redundancy by dropping features with no variability, drop columns with too many missing values, or even drop duplicated columns. But actually this technique, depending on your personal preference, on your strategy, you can also use them more as a pre-processing step. So this group really depends on your strategy, and I actually won't cover this one, even though it's one of the groups that I would like to mention here. Let's go to the other groups that I want to highlight. The first one is the correlation analysis. This is a very well-known group of technique that we use to simplify our model by keeping only the most informative features, right? And we can use lots of techniques. So for numerical features, for instance, we can use Pearson, Spearman, or Kendall, available in Pandas, for instance. For categorical features, we can use chi-squared, that is available, for instance, in scikit-learn. But actually, my favorite one in the past few times is one called phi-k, which is phi from the Greek letter, which is a technique introduced by some researchers from Amsterdam University a couple years ago. And this is a really versatile technique because you can use it on either numerical features and also on categorical features. And it's really simple to interpret. It gives you, in a single coefficient, you can have the correlation among all these type of features. It's built on top of some refinements of Pearson hypothesis testing. So it's really simple to interpret as well. The next group is time stability analysis. This group is really interesting because we usually use time stability analysis to detect drift in the monitoring phase after you deploy your models. But these techniques can actually be useful and very useful also during the development stage. Because if your feature drifts already in the development stage, it's likely that it will drift also you deploy your model. So detecting these unstable features beforehand can be really interesting as well. So there are lots of techniques to detect drift or to detect time instability, like population stability index, which is one that I've been using. This one is very popular, especially in banking industry. It's a really simple technique, and it's nice because it's available in this package called Feature Engine, which is a really interesting package for feature engineering, and also with these additional methods that are not available in scikit-learn. Also, Kolmogorov-Smirnov is another metric that is typically used to detect drift, and it's available, for instance, in packages like Evidently, if you use to detect drift, for instance, and many other methods and techniques to detect drift. And finally, the third group here, or the last group, is recursive feature elimination with cross-validation. This one basically balances performance with predictive power. So basically, we eliminate feature by feature in an iterativity process. Sorry. Assessing which are the most important features at each step and removing the less important features at each step. And there are also some alternatives to use. The recursive feature elimination, or RFECV module available in scikit-learn, I think is the most popular one. But I particularly like the one from Probatus package, which uses SHAP values as the main feature importance metric, instead of using the feature importance attribute that is usually available on the algorithms. Well, to make things more concrete, let's consider this practical example. So let's build a full feature selection pipeline using a real use case that we have at my company, with a data set that is composed by 72 features, 39 numerical features, and 33 categorical features. And as a good real use case, this data set is also quite imbalanced. We have around 1% of positive observations only. And let's then apply these first data screening methods, starting by the time stability analysis and then followed by the correlation analysis. And finally, in the remaining features, we will apply the feature recursive elimination. And please mind the order here, because as you noticed, I put time stability first, followed by the correlation analysis. And why this order is important? Because eventually, if you go to the correlation analysis first and you have a pair of features correlated, and one of these features is unstable in time, you can eventually drop the stable one. And then you apply the time stability analysis, you drop the unstable one, and then you completely lose that feature and that signal. So first, we eliminate all the unstable features, and then we proceed with the correlation analysis, so we will ensure that we keep all the signals that we want to assess in the recursive feature elimination step. Now let's see each of these three steps one by one. For the population stability index, for the time stability analysis, let's start with the population stability index. So it's given by this fancy formula here. It's simpler than it looks, but basically, to do the time stability analysis, we split our data into parts. One oftentimes called base, and the other one called test. And the idea here is that we compare the distribution of that particular feature in the base set versus the test set, and see how much distance they are from each one from each other. For instance, we can see this particular feature here. This N17 is a numerical, one of the numerical features on our model, where we first order it in time, so this is also important. You need to sort your data according to a specific time dimension that is relevant for your problem. And then we can see here that the base feature is more skewed towards the left part, while in the test set, the feature is skewed more towards the right part. And this gives us a applying the formula, this gives us a PSI of 0.81. But how can we know? Of course, this as I mentioned before, this method is available in the feature engine package, which is a really nice package, through this drop high PSI features module. That's how I computed this. And how can we know that if this 0.81 is high or not for this particular feature? Well, there are some rules of thumb. So for PSI, we typically use a threshold of 0.25, meaning that if your feature has a PSI larger than 0.25, it's safe to assume that it drifts, so you can discard that feature. Moving on, the next step is the phi-k correlation. So phi-k is basically, as I said, is a correlation coefficient, a correlation test that is very versatile. So we can, for instance, build a very typical correlation matrix to assess the correlation among all of our features. And as I was mentioning before, this is super nice because we can see, for instance, the correlation between all the numerical, among all the numerical features, but also among all the categorical features. And finally, and more interesting, the correlation between numerical and categorical. So phi-k does that, does all of that in a single module. Of course, the darker the point is, the more correlated it is, as we usually interpret this kind of correlation matrix. We can combine this phi-k correlation coefficient together with the drop correlated features module, also available in feature engine, where you can pass any correlation function that you want to discard correlated features. And again, as a good rules of thumb, we can consider that a correlation, a pair of features with a correlation higher than 0.8 is safe to assume that it's highly correlated, so you can discard that feature. Of course, this threshold, you can adjust accordingly, because it is really associated with the kind of algorithm that you are using. So for instance, if you are using algorithms such linear models, like logistic regression, for instance, they are more prone to correlation effects. So 0.8 perhaps is a good value. But if you are using like tree-based models, well, they are less susceptible to correlation effects in general, so you can be more strict and use, for instance, 0.9 or an even higher value if you want. And finally, the recursive feature elimination procedure. let's just see how it works in general. So it's an iterative process. We basically train a model with some set of features, with an initial set of features. Then we evaluate, here using cross-validation, which is very important because we are using only training data to do all this process, leaving our holdout set or our test set untouched until the very end of our model development. And then we sort the features by importance. And here, I'm using SHAP values instead of the default importance of the algorithms. And why? Because SHAP values usually use the predictions or your validation set to estimate the importance, and not the training set as typically is used by the algorithms to estimate importance. In general, to make our models more interpretable and more explainable, we should really pay attention to the predictions and not to the training, to what was fitted in the training in terms of importance. And that's why SHAP values here makes the difference. And finally, we remove the last important feature, and then we repeat the process again. We can define the step, of course. The lower is the step, the more refined is your process in general. This, of course, depends on how much resources you have available. But here, I did all this process using removing one feature at a time. Again, we can use, as I mentioned, we can use the Probatus package, which is a really nice package developed by, I think, the ING team. It's a Dutch bank. And I'm using here one of my favorite algorithms, which is XGBoost. And it's really simple to use. So we can basically define our model, we can define our cross-validation strategy, and we can define the step, as I was mentioning before. Here I'm removing feature by feature in the elimination process. And then in the end, we have this plot. So if we focus in the validation curve, the blue one, we read this plot from right to left, we can see that we have almost no changes in the performance metrics until more or less 15 features. When we can notice this kind of elbow pattern. And then we think that we can conclude here that 15 features is indeed a good number to use here. Well, putting all together, we initially started with 72 features. We then applied this first screening method, dropping 17 features, 4 due to high PSI and 13 due to high correlation, followed by the recursive feature elimination, where we discarded 40 features, ending with a set of 15 features. Okay, and that's basically was the result of our feature selection pipeline. Okay, now the tough question. So should we go for the default parameters, or should we do some hyperparameter tuning? Well, this question is really can be really tough, but again, let's try to understand why should we care about hyperparameter tuning. Again, we can see this in three different perspectives. So in terms of performance, we want to improve our do hyperparameter tuning can help us improving the overall accuracy or performance of our model. It helps reducing overfitting and enhance robustness to predict in new data. It can help us to improve interpretability as well, so it simplifies the model, helping the model highlighting the key features or paying attention to the key features during the training, and also clarifying the decision path, helping perhaps making the model less a black box. And finally, efficiency, of course, depending on the parameters, you can speed up your training time, optimizing resources, and improving, of course, scalability if you eventually have a really large data set. Some common techniques here are essentially grid search. I think this is the most popular one. It's very simple and straightforward, but it's not advisable at all because it's very expensive computationally speaking, depending on how many hyperparameters or the size of your hyperparameters range. It's available in scikit-learn. A better alternative is random search. It's more efficient, especially when you have a large number of hyperparameter tuning, but it still be computationally intensive, and it really depends on computational resources that you have available. This is also available in scikit-learn. And finally, the one that I like the most is Bayesian optimization. It's more efficient and eventually leads to faster convergence and finding eventually better hyperparameter tuning. It's a bit more complex because it eventually requires some understanding of probabilistic models, but it's a really nice solution. You have here, for instance, Hyperopt and Optuna as good candidates on how to use that. But Optuna actually is my favorite one, especially because it has nice integration with scikit-learn models and scikit-learn tools, as for instance, Optuna Search CV. So let's see it in action. Basically, I'm combining again Optuna and optimizing my XGBoost classifier. You can use it in a very simple way. So basically, you define your parameters space using Optuna's built-in distributions for integers, floats, and categories. And then you basically instantiate the object as you would do for random grid search or random search, for instance. And after that, you get this really nice curve where you can see the optimization path. We can see that Optuna converges really fast. Around 50 trials, it already converged to the optimal solution. And also, it provides this nice feature importance plot where you can, from where you can have some insights on which hyperparameters Optuna used the most to optimize your solution. So wrapping up, we have seen some feature selection techniques to enhance your model performance and also some hyperparameter tuning methods to improve also performance, improve interpretability and efficiency of your models. Basically, and what we can learn from this, we should always aim between performance and explainability. I think this is really important if we are applying our models into a business context. And try to go beyond the basics, try to explore new techniques, new methodologies. I think it's super nice. Eventually, it can be time consuming, but once you find a good set of techniques, you can reuse it for different projects. So I think this is also really nice. And finally, this is of course an iterative process. It's a trial and error. But yeah, I think we should always try to keep improving and trying different techniques and different methodologies. And just a final thought about the first question in the meme: is machine learning in the age of Gen AI, is it still relevant? My 2 or perhaps 3 cents here is yes. I think there's still room, lots of room to improve our models, because those models are still delivering significant values to our companies and to our businesses. So while this is true, I think we should always try to improve those models and investing on such techniques. Also, we should always try to ensure our model efficiency and interpretability. I think this is some really nice things to aim, while at least yet Gen AI might not fully cover. And finally, I really believe in synergy and not replacement, so I really think that combining efficient Gen AI techniques with our traditional machine learning models can really boost our models and our solutions. That's it. Thanks a lot. And yeah, I'm curious to hear your questions and comments.